Okay, so today's new topic is more tests to determine convergence or divergence of infinite series. Now, at this point in the semester, sometimes students get a little bit lost. I have to mention this to you because there's going to be so many tests introduced, and you just got a handout today summarizing all the different tests. It's basically a 2-page handout of all the different tests. It's easy to feel a little bit lost. You know, if you feel like that way, you know, you're not the only one. A lot of students tell me in the beginning, at least in this chapter, they feel not so comfortable. Now, I want to give you a little bit motivation as to where we're headed with these. So perhaps they'll help you get through these next few sections until we get to the end, which I think is the most interesting part of this whole chapter. I also think in geometric series was very interesting, but also the ending. The ending is called Taylor and Maclaurin series. And it's a very, very fascinating part of the chapter where we're going to find what I call the clone functions. For example, think about sin x. You know, it seems like such a mystery function. Or think about e to the x. You know, when you punch in e to the x to your calculator to evaluate e to the power of 0.2, does anybody have a clue what the calculator is doing to evaluate that value, e to the 0.2? No clue, right? It's like a black box function. But if you were plugging in something like 3 to the power of 5, it's clear, right? You multiply 3 times 3 times 3, 5 times. Now, what if you were taking a number, let's say 5 to the power of 1.72, something like this? It would evaluate it for you, but what is it doing? You know, so when you are doing exponential functions, when you're doing a sine of certain angles, we all know the important ones like pi over 4, pi over 6, etc. But what if you want to know the sine of 1.265 radians? How did they come up with these values? So we're going to get actually some answers to those questions. We're going to understand these functions better by studying what I call their clones. So for example, when we study sin x, we're going to learn that sin x can be written as a polynomial. We're going to learn like sin x might be something like this. X minus x to the third over 3 factorial plus x to the 5 over 5 factorial, etc. Who knew sine functions or any trigonometric function, something that is so complicated? Think about exponentials, logarithmic functions. Who knew that they had their equivalents in terms of these elementary functions? And elementary functions are powers of x, like polynomial functions. Those are easy. Why are they easy? Because if I wanted to evaluate sine of 1.7, I'm stuck. I have no clue how to evaluate that, right? But if I want to evaluate, plug 1.7 onto the right-hand side. 1.7 minus 1.7 to the third over a number plus 1.7 to the 5 over a number. We know how to take the fifth power, right? You multiply the same number 5 times by itself, right? In other words, the right-hand side function is just 4 operations: add, subtract, multiply, divide. Everybody knows how to do that, right? Once you're through elementary school, you know how to do that. So what we're going to do is we're going to convert these complicated functions into their elementary equivalents. Polynomial functions, they have fancy names like Taylor series or Maclaurin series, but they're actually very simple functions. And what is the advantage of doing that? Well, you can do all sorts of things. You can prove things you couldn't prove in the past. You can evaluate these functions. You can understand how calculators are working, like when you do sine of 1.7. In the past, we had no clue. And also, you can do things that you couldn't do. For example, the integral of sine of x squared, or I can write many other functions. This is one example. No matter how many techniques of integration you study, there is no answer to this. There is no antiderivative for sine of x squared. But if you can convert it to its infinite series expansion, from there, we're going to be able to get some answers. So just hang in there until the end of the chapter where we're going to get to these infinite series expansions of these mystery functions. And you're going to see I'm going to try to pull some examples from physics, from proofs, etc., that things you couldn't do in the past, we're going to be able to do them once we get these clone functions of the black box functions. Okay, so for now, we're headed in that direction, but it's going to take us about 2 weeks to get there. So we're going to spend this week and middle of next week, I think, until we can get and form those infinite series function for pretty much every function you've seen. You know, we're going to form an infinite series expansion. But to get there, first we have some simplistic tests. One is called the integral test, the other one is called the comparison test. And we're going to take a look at both of those today. So what I'm going to do today and next time is I'm going to cover 2 sections from the book on each of the days. Okay, so this is 2 sections in one day. We're going to do the same because I'm trying to fast forward the part that I don't think is that important and that significant, trying to get to the part that I think is most important before I lose you, before you get lost in the details of the stuff. Okay, so let's take a look at integral test, the statement of it. I think I have a newer version. I thought I had a newer version of it. Let me see. Okay, give me just 1 second. See if I can find it. Okay, first of all, the integral test should be listed on the handout that you just got. Okay, looks like I need a slide, but I don't have it. Let me bring it up a different way. Just give me 1 second. Okay. Okay. Okay, so we are going to look at this, first of all, the statement of what is called the integral test. Now remember, with the n-term test, it wasn't a very powerful test. All it could tell you was if something diverges, if the limit doesn't go to 0, but if it goes to 0, it failed. The test was inconclusive. This will give you one more tool. And here's the statement of the test. It says, if you have a positive continuous and decreasing function, basically it's telling us that when you're trying to determine whether a series converges or not, say that series is this one right here. What you should do is you should take the integral of that sequence portion. Take the integral. So for example, if you were trying to determine summation of 1 over n, if this series converges from 1 to infinity, it's saying instead of that, take the integral of 1 over x from 1 to infinity. And further it's saying that if the integral converges, then the series will converge. If the integral diverges, then the series will diverge. So that's what we're going to do. And to give you a little bit of explanation where this comes from, just take a look at these 2 graphs. Don't worry about the writing that much. Just take a look at the graphs. The integral of something, if it's a positive function, it's the area under the curve, right? The integral of something is the area under the curve. So if you were to find the integral of this function from 1 to infinity, you would be finding the area under this curve from the point x equals 1 to infinity. That would be the area under this curve. Okay? Now, what would be the summation, though? What would that represent? The summation of that would be, for example, a sub 1 would be basically the area of the first rectangle here. Okay? A sub 2 would be the area of the second rectangle, etc. So what we're saying is, we're saying somehow, if that area under the curve, from that point on forward, if that area is finite, then the summation of all those little rectangles, that's going to be finite as well. It makes sense, right, looking at the graph, because that area is actually smaller. Some of the little boxes is actually smaller than the area of the under the curve. And conversely, look at the other graph now. Look at this graph. If I was to take the right endpoints, like here I took the right endpoints to get the heights. If I was to take the left endpoints to get the heights of my rectangles, then I get a situation like this. So this is, for example, a sub 1. The next one is a sub 2, etc. So in the first picture, I took the right endpoints to get the heights. In the second picture, I'm taking the left endpoints to get the heights. But still, the integral of the curve will be the total area under this curve. The sum, the infinite sum, like a sub 1 plus a sub 2, etc., that will be the sum of all these rectangles' areas. So in this case, we can see that if the integral is infinite, then the sum of those rectangles they're actually going a little bit above the curve, so they're even a little bit bigger. In that case, the sum of the infinite series will be infinite as well. Okay? If you're more interested in the details of the proof, please see the textbook. But again, I just wanted to give you at least some intuitive understanding about why this test works, because there's an intimate relationship between the integral of a function and this, a summation, because the integral is, after all, a summation. So all it's saying is if the integral converges, the summation will converge. If the summation, if the integral diverges, the summation will diverge as well. Okay, so let's use that test with this first example. Summation of 1 over n. Based on the integral test, what can we say about this series? Does it converge? Does it diverge? Or is the test inconclusive somehow? When I look at questions like this, I always begin with the n-term test, and I want you to get into the same habit. Begin with the n-term test. What does the n-term test say about example number 1 here? What does the n-term say? Take the limit as n goes to infinity, right, of 1 over n. So first we're using the nth term test. So we're taking a limit of the sequence portion, right? So what is that test telling us? That limit is 0. So what does that test tell us? No conclusion. So basically that test fails, right? So we got to apply another test. Remember, limits being 0 is a necessary but not a sufficient condition. Yes, it's going to 0, but there are other things like how fast is it going to 0? That's also very important. So let's apply another test. We just learned the integral test, so let's apply that. So take the integral of 1 over n as n goes from 1 to infinity. And usually the way we write this is, usually we write it like in terms of x, like 1 over x dx. You could keep it in n if you wanted to, but we're just more used to working with x for the functions. Okay, what is the integral of 1 over x? ln of x, exactly. We're going to go from 1 to infinity. Okay, now you have ln infinity minus ln 1. What do we know about ln infinity? Where does it approach the ln function as n goes towards infinity? The ln function, it keeps growing, right? Slowly, slowly. It's one of the slowest increasing functions, but nonetheless, it's an increasing function. It's growing, growing, growing slowly. So where does it go then? ln 1 is 0, so it's going towards infinity. So since the integral goes to infinity, what can you say about the original question? That one goes to infinity as well. So let's write our conclusion. By the integral test, the original series diverges also. By the integral test, the original series, which is from 1 to infinity of 1 over n, diverges also. Because we learned that the integral of the function and the summation of the corresponding sequence, they will both act the same way. Okay, how about number 2? First, I always recommend you to apply the n-term test. What do we get by the n-term test? Exactly. Once again, by n-term test, the limit of the sequence is 0. So that test by itself is not enough to answer this question. So use another test. Let's use integral test once again. That's the only other one we know so far. So let's integrate 1 over x squared dx from 1 to infinity. Okay, what is the integral of 1 over x squared? Think of it as integral of x to the minus 2 dx. X with negative 1 over negative 1. In other words, negative 1 over x. So now we have negative 1 over infinity minus negative 1 over 1. Where does, again, when I write 1 over infinity, anytime I put infinity, as if it's a number. It's really, we're taking a limit. It's a shortcut notation that I'm using. 1 over infinity really means 1 over x as x goes towards infinity. So what do you know about that quantity? If the bottom keeps getting larger, the top is a constant, what is the ratio going to be?
Well, anything on infinity is 0.
Correct. It will approach to 0. So that part is 0. So what are we left with then? Negative of negative 1, in other words, positive 1. So the answer is positive 1. Now, what we're saying is the integral goes to an answer. We don't really care about what that answer is. I'm not even going to box it in because all we care about is that it's a finite number. It's a finite value. So what can you tell me about the original series? Therefore, by the integral test, the given series does what? Converge or diverge? If the integral is a finite answer, that means it converges basically. It's a finite answer. So what can we say about the summation? The original question converges also. Basically is a finite result, but the way we usually represent it is we say, i.e. it converges. A series converges. If it goes to a finite answer, we say the series converges. Now, does it converge to the same answer? That's another question we could ask. Do you think that this infinite sum is going to be exactly 1? The answer is no. Because remember those overlaps and underlaps? They're not going to go to the same exact answer, the area under the curve and the sum of those rectangles areas. But all we know is that if one is finite, the other is finite. If the integral is infinite, the other is infinite. But they don't have to be the same answer. As a matter of fact, this happens to be a famous summation, and a very famous mathematician in the name of Euler, I believe, who found what the sum was. It's a very complicated proof, but I think he showed that I think the sum is equal to pi squared over 6. At the moment, we're not going to worry about what the sum is. All we're saying is, if you were to add up all the terms of the series, would it be a finite answer or would it be an infinite answer? In this case, we're saying the answer is a finite answer, and that's all you have to worry about. You don't obviously have to know what it sums up to, or that it sums up to this weird-looking number, or surprising. Right, that is an interesting but complicated proof. If anybody's interested, you can look it up. I'm sure it's available on the internet. No, it is not equal to 1. I can tell you that right now. The integral and the infinite series, they're not going to go to the same number. All we know is that they both converge or they both diverge. Okay? Now, does it surprise you? Are you going to be able to sleep tonight after you've seen this result? Take a look at this, Summation 1 over n. Let me write those numbers to see what they represent, okay? 1 plus 1 over 2 plus 1 over 3, etc. We're saying this is going to go to infinity, right? But summation of the 1 over n squared, which is 1 plus 1 over 2 squared plus 1 over 3 squared plus, etc. We're saying that's going to be a finite answer. Does it make any sense to you that, one is finite, one is not? How could you explain this so we could live with this result? They look so similar, but there is a difference between these two series, right? Stephanie, you seem like you have maybe an idea, or why do we think that this one is a finite and where this one was not a finite answer? Exactly. At least we know the second one, the bottoms are bigger, so the ratios are smaller, right? In other words, the second series, the terms are approaching to 0 much faster than in the first series. Still, there is no guarantee, of course, by looking at it, but if we apply a test, then we know if it's going to converge or not. Now, I'm going to see if I used to have a folder here where I use Scientific Notebook to show something. If I can find it today, I'm going to show you today. If not, I'm going to come back to it. Okay, there we go. Example of a divergent series and a converging series. Let me see. Version 2. Let me go to this one. I don't remember which one was my last version. Okay. No, I don't want version 2. I think I'm going to go to version 1. No, I don't want that one. Okay, possibly. Okay, this is not a bad example, actually. Okay, here's what I did. Take a look at these two series, okay? Look at the first one, 1 over 3n plus 1. That's kind of similar to 1 over n. Okay, actually, we're going to talk about comparison today. We're going to make it resemble to 1 over n because the dominant terms are like 1 over n. Take a look at the second series that I have here, n over 3n cubed. Look at the dominant terms, n over n cubed. That's going to behave like what? N over n cubed, which is the same as 1 over n squared, right? N over n cubed. So this series is very much like 1 over n squared. We just saw that one was convergent, right? And the first one is 1 over n. And this is what I did with Scientific Notebook, which, as you know, is a software. It's a technical writer, etc. I defined a sequence of partial sums. So what I did was look at the first one. I'm adding the first k terms. Okay, so S of k, I defined it to be a summation from 1 to k. For example, if x is 10, it's really k is equal to 10. If k is 10, I'm going to add the first 10 terms, okay? If k is 20, I'm going to add the first 20 terms, and so forth. If it converges, the number should be approaching to a unique answer, right? Okay, let's take a look. It's going to let. When you add 10 terms towards 100 terms, do they seem to be approaching to a unique answer? They keep getting larger and larger and larger, right? Now look at the next example. It's going to let me scroll down here. Okay, scroll down. This is the one with 1 over n squared type of example, right? Okay, take a look at that one. After 10 terms, it was 0.429. After 20 terms, it's this. Does that one appear to be approaching something?
Yeah.
That one is like hovering around 0.45, 0.456. Let me check something. I define a function here. Okay, I want to show you what happens with 1,000. Okay, so let me define my function. I'm going to define this as my function. There's a defined thing up here. F of x equals to what? So I'm defining it just to make sure. I'm going to look under the magnifying glass. And let me delete the other one so it doesn't get confused. Okay, and let me try to enter. I'm not sure if the keyboard is working here. Okay. Okay, I'm going to try S of 1,000. I wanted to add 1,000 terms of this series for me. Just to see if there's a pattern, if this is really converging. So I'm going to go to equals to what to evaluate this numerically. After 1,000 terms, it's still stabilizing around 0.46. You see, from 100 to 1,000, it really didn't add that much more. Whereas the other one, the one that was diverging, let's take a look at that one again. You know, at 50 it was this, at 100 it was this. Once again, what if I define it again as, I think capital S is, this one, lowercase letter s is the other one. So let me also do that one then. So what if I did capital S at 1,000? So now we're going to make this series add up 1,000 terms. And I'll go equals to what numerically? You look at it, 2.34. So it's not really stabilizing at a single number. You see, so this is how you can see numerically that a series is diverging. Yes, it's diverging very slowly, though. This is supposed to go to infinity, but it's going very, very slowly, as you can see. But it's not going to a unique number. That's when we say something diverges. Whereas the other one, very soon after the first, 10, 20, it was starting to stabilize around 0.45, and it looks like it's really going towards 0.46. Okay, let's go back to our integral test with the two examples there. A subtopic of the integral test is something called p-series. In other words, we just did 1 over n, we just did 1 over n squared. Now, you don't really have to apply the integral test every time you see these things because there are patterns that are emerging. So if you see those patterns, you can make use of them in the future and you can save time. So once again, Earlier, we just did what summation of 1 over n. Then we did summation of 1 over n squared. The question is, can we draw any conclusions out of this? What if I did summation 1 over n cubed? Do you have any guesses what's going to happen there? Summation 1 over n cubed. Do you think it's going to converge or diverge? The terms of 1 over n cubed are going to be even smaller than these guys, right? The 1 over n squared terms. That one was already a finite answer. So any guesses what 1 over n cubed is going to be? The summation of 1 over n cubed looks like this. 1 plus 1 over 2 to the third plus 1 over 3 to the third plus 1 over 4 to the third, etc. Now you already know summation 1 over n squared converges, right? So can you tell me anything about summation 1 over n cubed? It also converges because the terms of this series are even smaller than 1 over n squared. Well, if this one was a finite answer, and this is even smaller than that, that one also converges. How about 1 over n to the 4, 1 over n to the 5? Do you think those converge or diverge? They all converge. Basically, the moment the power is, at least based on these examples, 2 or higher is converging, right? But this one actually says, look at this, the theorem. It says summation of 1 over n to the p actually converges. It says as long as your power p is greater than 1. We knew it diverges for 1, right? So this is saying even if it was 1 over n to the 1.1, it claims that it's going to be convergent. If you like, we can go and test it, okay? Summation 1 over n to the 1.1. So I will change this function, and I will make it 1 over n to the 1.1. Okay, so according to the test, what should happen to this? Read the P-series test. It's also in your handout, right underneath the integral test. Please read that. It says as long as that power is greater than 1, what does it tell you about the series? As long as that power is greater than 1. What I'm going to do is I'm going to redefine this function since I've changed it. So I'm going to go to function definition, f of x equals. To confirm it, I'm going to look under the definition right there. It took the new definition. This is my lowercase letter s function. Again, the claim is that, according to the P-series test, it says as long as the power is greater than 1, the infinite sum of that series is supposed to converge, right? Well, let's check that claim. So s of 10, let me go ahead and evaluate this. I just had to click, I think, the equals what? The number sign. Okay, it's 2.68. Adding the first 10 terms of that series. Okay, what if I was to add the first 20 terms of that series? When it evaluates something, it gives that extra notation. Don't worry about it. Okay, the next one, 3.8. The next one, 4.2. It's not easy to see this one, obviously, from a numerical perspective. Let's do 1,000. Interesting. This one stumps me, I have to say, because I really expected to be able to observe it. But I think this is a series that converges so slowly that numerical methods are really not giving a good result here. But I'm going to show you the proof. And once we see the proof, there is no questioning. The proof will show us that this is actually, this series should be converging. It's just converging very, very slowly. And what if we did like a really large number? How about let's do 10,000 and 100,000. Let's just really in large numbers. So let's do 10,000. Let's do 100,000. And should we do a million? Okay. It may take all day, but we'll see how long it takes to calculate it. This is a pretty powerful program, so I'm pretty confident it's going to be able to do it. Okay, so let's do S of 10,000. If you add up the first 10,000 terms, let's see what it gets. That was actually very quick. How about this one? S of 100,000. Okay, it was, oh, no, it didn't take that long. 7.4. A million. Here we go. It didn't even show the waiting sign. I don't think so. I think this, let me try one more time. Maybe you can accept it. Aha. This program is really, really powerful. I've seen it in action before. Now, I don't know how long it's going to take, but but it shouldn't matter. Okay, let's do 500,000. Let's do, I think the computer may have shut down on us. Okay, we were trying maybe too much. But you know, one year I was able to do more than 1 million in this class, so I was confident it's going to work again. But I think this time we may end up crashing the computer. Okay, while it's working, let's go back to our notes. I'll go back to it in a little bit. Maybe we'll get something, okay? But I can show you that actually when when p is greater than 1, it's actually supposed to be convergent. And here's how the proof goes. I want to show you the proof so that you don't think I made this out of nowhere. I'm not making this up. It's a theorem, and it's guaranteed that as long as that power p is greater than 1, it's supposed to converge. How does it work that way? Let's kind of analyze it a little bit, okay? So we're going to apply the integral test. Okay, integrate, instead of n to the p, I'm going to integrate x to the p. Okay, what is the integral of 1 over x to the p? First, let's rewrite it. Okay, how do you write 1 over x to the p? It's x to the power of negative p, right? Simple enough. Okay, how do you integrate x to the power of negative p? Think of p as 5 or 1.1 or whatever it may be, right? You would add 1 to that power and divide by the new power, right? So when you integrate that, it's going to be x to the negative p plus 1 over negative p plus 1. Now, the only way this is going to converge is if this x to the power ends up being in the denominator. Because if it's in the denominator, as x goes towards infinity, what's going to happen? Infinity is going to go in the denominator, and 1 over infinity goes to 0, right? So what is the only thing that would push this x into the denominator? What would that power have to be? The negative p plus 1? What would you have to say about negative p plus 1? Think of this. If you have x to the negative 3, this will push it to go down, right? It'll be 1 over x cubed, right? So what do you want this power to be so that you end up being in the denominator? You want that power to be what? Less than 0. Because if it's less than 0, it's going to be like x to the negative 3. It's going to push it to the denominator, right? And if it ends up in the denominator, as you plug in the infinity, as x goes to infinity, this will go towards 0. So that's the only way this is going to converge. And just solve that inequality. If negative p plus 1 is less than 0, so let's do that. If negative p plus 1 is less than 0, put p on the other side. That means p is greater than 1. So if you have this situation, it says that it's going to be convergent. And in the case of 1.1, because the scientific notebook wasn't very, it really didn't show us anything. It basically, we couldn't conclude easily. It almost looked like it was going to diverge, right, from the way it was looking. So let's apply the integral test to 1 over x to the 1.1, because that's important to see. So 1 over x to the 1.1. So in that case, we really couldn't see that much from the numerical approach. So this is the same as the integral of x to the negative 1.1. Okay, how do you integrate this? Add 1 to the power, right? Which is going to be x to the negative 0.1, and divide by that power. And we want to go from 1 to infinity based on the integral test. And as long as there's a negative power, it comes down, right? It comes to the denominator as x to which power? I put the negative up front, by the way. Exactly, because x to the negative 0.1 on the top, when it was brought on the bottom, it became x to the positive 0.1, right? Think of 0.1 as 1 over 10, okay? So we're talking about the 10th root of x on the bottom, okay? Where would the 10th root of x go to as x goes to infinity? 1 over the 10th root of x. It still goes to 0, right? So, and then you would plug in the 1, and then you're going to end up with a finite answer here. So this is going to be a finite answer, basically. And we don't really care what it is, but we know it's going to be a finite answer. So if the integral is finite, then that means the series should be finite as well. So as you can see, trying to get an answer numerically, even with a program as powerful as Scientific Notebook, is tricky. It doesn't always tell you what it's going to be doing in the long run as n goes to infinity. So that's why these tests are really important. But I have to say, for the majority of the series that we're covering here, you can get a pretty good idea using Scientific Notebook as to whether it's converging or diverging. But this one was an interesting one. It really stumped the Scientific Notebook even. Just out of curiosity, I'll go back there for a minute. It did it, but it still looks like it could be diverging, right? Look, it added up the million. It's like 8.07. But if all you had was numerical methods, if you didn't have analytical methods of calculus, you might look at this and you might say, wait a minute, this looks like this is going to be divergent. But we have solid proof. We just proved the theorem that this should be convergent, right? It's just that it's hard to see it, apparently, from the table approach. But I'm curious. I'm also going to put 5 million. And we're going to let it run, and we can come back to it. Okay, I hope the computer doesn't crash. One of these days it will crash on me, I know. Okay. Okay, so we'll let it run over there while we do our thing back here. Okay. Okay, another topic. It's all related today. So far we did, I'm sorry. I want to finish one more example with the p-series. We did 1 over n to the 1.1, but I want to do another one. Can you tell me quickly, does 1 over square root of n converge or diverge? Use this result up here. We're using this result to answer this question. 1 over root n is the same as 1 over n to the 1/2, right? The p-value here is 1/2. It is less than 1, so it falls into this category, right? Therefore, the series diverges by the p-series test. Okay, and how about the next one? I can rewrite this as what? That is n times root n. It's not the nth root of n, it's n times root n. And that can be written, as Chris suggests, as n to the 3/2 as n goes from 1 to infinity. And once again, this is a p-series, right? So as long as you can recognize it, you can apply the p-series. If you forgot about the p-series, you don't recognize it, apply the integral test, right? Because the n-term test is going to be inconclusive here also. Okay, so this is a p-series with p equals to 3/2 because it is greater than 1. What is our conclusion? The series converges. Okay, I'll check on our Scientific Notebook on this side. I think it's still going like last time. It disappeared for a while, but maybe it'll come back. So let's just let that run. Okay. So now a related topic called estimating an infinite series. And this is also in your handout. Look on the bottom of the second page. On the bottom of the second page, under estimating infinite series. You see that? It's right here. Okay, this is a really neat theorem because it tells us basically that. It tells us that when you're adding infinitely many terms of a positive series, I think the assumption here is that we have a convergent series, that you have an integral that is a finite answer. Suppose you have a convergent series, okay? And suppose you're trying to estimate what is the sum? What is this infinite sum? This theorem is really neat. It tells you you don't have to worry about adding infinitely many terms. All you have to do is add up finitely many terms. For example, in this case, how many terms did they add? K terms, from 1 to K. But there's going to be an error involved, right? Obviously, if you didn't add up infinitely many terms, if you add up, let's say, the first 100 terms, there's going to be a difference between your answer of adding the 100 terms and the actual answer of adding infinitely many. But this theorem tells you how much error you would expect in that difference, the difference between the finitely many terms and the infinitely many terms. It's telling you that that difference, which we call error, the difference between summing infinitely many versus summing finitely many is the error. It says that that's going to be less than the integral from k to infinity. So if you add up the first 100 terms, take an integral from 100 to infinity, and it tells you the error will be less than that. And maybe I can show you why this theorem works through a picture. I will go back to that original picture I had earlier. Let's see, from the early on chart. Okay, look at this first picture. Let's say we added up the first, maybe I can look at this one. So the general idea, again, it's not going to be a solid proof here, but the general idea is you're trying to add up all these areas of the rectangles. That's the sum of the series, A1, A2, A3, A4, etc. Okay? But suppose you added only the first four. This one, this one, this one, and that one. The theorem is saying basically integrate the function from 4 to infinity, and it's saying that all the things that you did not add up is going to be less than the area under that curve. That's what it's telling us. So let's go and do an example. Wow, it did come up with an answer. Still, it's 8.44. Now, for the first time, it's a little bit closer, I think. The values are getting a little bit closer. 10 million. How does that sound? Okay, let's let that running. Okay, so we're doing this is called the estimation theorem for positive series. So let's do an example to see what we mean by this. Here we go. Estimate the given series using the first 5 terms, and then comment on the size of the error. So instead of adding up the infinitely many terms, we're going to add up the first 5 terms. That would be a lot of big time-saving strategy. But then we need to have an idea how far off are we from the actual answer. To answer that, we're going to use the estimation theorem. Okay, so let's first of all add up the first 5 terms. I'm going to call that S sub 5. S sub 5, the sum obtained using adding the first 5 terms. Plug in 1 for n, then plug in 2 for n, plug in 3 for n, plug in a 4, and plug in a 5. So let's add up the first 5 terms. And let's see what we're getting.
Okay.
What do we get for this, anybody? One point something, right? Because the first term is 1, I think. Oh, it might be more than, I guess, 1, but it cannot be less than 1, basically, right? So again, very roughly speaking, we're saying, yeah, we're going to be adding infinitely many terms or infinitely many rectangles here, in a sense. But instead of doing that, we're adding, let's say, the first 3, let's say. We're adding the first 3. This one, this one, this one. And what did we miss by not adding all the other rectangles from that point to infinity? What did we miss? What we're saying is, whatever we miss is going to be less than the integral from that point forward of this function. So if you just could find that integral, the error that you have in estimating this infinite series by using the first 3 terms is going to be less than the integral from 3 to infinity. In this case, we have 5 terms. So if we add up the first 5 terms, what do we get? Anybody who got something? 1.0367? Okay, 1.036. I want a few more decimals. So 366 and then another 6. Okay, let's leave it with that one at the moment. So we're saying at the moment that the sum of the first 5 terms is roughly 1.04, roughly speaking. But how big is the error? We didn't add up infinitely many terms here, from 5 and up or 6 and up. We didn't add those. So some people call that the error, the difference between the infinite sum and the and what we got. Some people call that the remainder. They might call it like R sub 5, the remainder, meaning everything after that point. So the error will be, according to the theorem we just learned, the error will be less than what? The error will be less than, look at your theorem, less than the integral from whatever the k was to infinity of that function. So in this case, k is 5. So the integral from 5 to infinity of, instead of 1 over n to the 5, I'm going to put 1 over x to the 5. So basically, we're saying, if you just found that area, that's going to be an upper limit for what we're missing. In this case, from 5 to infinity. Okay, so let's integrate this from 5 to infinity. So we're integrating x to the negative 5, right? And that integral is x to the negative 4 divided by negative 4. Okay, what will I have, first of all, if I plug in the infinity for x? One over 4 times x is replaced with infinity. X is getting larger. Where does that go to? Basically, you have like 1 over infinity. Where does that go to? 0. That goes to 0, right? So if you plug in infinity, you get 0. Minus plug in 5. We get positive 1 over what? Did you get 1 over 2500? Which is the decimal form. 0.0004. Not bad, huh? We didn't add term number 6, 7, 8, 9, 10, all the way to infinity. But what have we missed by not adding all those extra terms? Whatever it was less than 0.0004. So if we took this example to Scientific Notebook, this would have converged very fast. Basically, after you add the first 5 terms, the first 10 terms, you would have started to see a pattern emerging there, okay? Any questions about this before we do it? Yes. Courtney? The significance of the answer? Yes. What this 0.004 is saying is, let me see if I can pull everything further down so I'll get some extra room to write that more clearly. Okay, good. Okay, so what we're saying is this. We're saying the difference between the infinite sum and from 1 to infinity of 1 over n to the 5, and the one that we just did, we added the first 5 terms, right, from 1 to 5 of 1 over n to the 5. We're saying that that difference is going to be less than 0.0004. So we call this the error. The error will be less than 0.0004. We can also write it like this. Basically, we are saying that this infinite sum is going to be basically less than or equal to, what was the answer we got for the sum of the first 5 terms? 1.0367 plus the error, 0.0004. So we only added the first 5 terms, but we know that the infinite sum is going to be no more different from the sum of the 5th terms, no more than 0.0004. So that represents the error. That represents basically we did not add up from 6 to infinity, right? We only added the first 5 terms. We're saying what we missed by not adding up all those many terms is going to be less than 0.004. So this one is a very fast converging series. Just adding the first 5 terms is giving you a great deal of information. The other one we're doing was a killer, right? That one, I can do the math for you if we have time later today. Chances are you have to add up like the first 40 million or something to come up with an error that small. Let's see what it's doing right now. Wow. It's getting somewhere. It went from 8.4 to 8.6, and we added up almost like 9 million terms, or yeah, we added like 9 million terms, and it only went from like 8.4 to 8.5. So it's starting to perhaps converge somewhere, but again, numerical is no proof. We've got to do it with the test to be for sure. Okay, how about this next one? Same question was asking you a little bit differently. Now I'm giving you the error. So I'm giving you a series, and I'm saying, how many terms should we add so that this infinite sum can be estimated by an error less than 0.001? How many terms should we add? So let's pretend we're going to add k terms. let's say we're going to add the first k terms. We don't know what k is. But how do we find the error? We know the error should be less than it actually says less than or equal to, so maybe I should adjust that. Okay, less than or equal to. What should I put here? Integral of what? K to infinity of what function? N to the 3 halves, which is the same as, in our case, x to the 3 halves. So usually when we integrate, we like the variable x for some reason. We're just used to it, I guess. And we want this to be less than, we want the error to be less than 0.001. So let's integrate this. What is the integral of x to the negative 3 halves? What's the antiderivative of x to the negative 3 halves? Add 1 to the power, right? So what do we get? So the plus 2 over 2. And you get x to the negative a half, right? I'm anti-differentiating basically this function here. I'm anti-differentiating it. What is the antiderivative of it once again? Add 1 to the power, x to the negative a half, divide by that power, which is division by negative a half. That means multiply by negative 2. And the limits are from k to infinity. Any questions about my antiderivative here? Any questions? Okay. I'm going to rewrite it. This is negative 2 divided by root x. Would you all agree with that? Because x to the negative a half means put it down and it becomes x to the positive a half. And now what is this going to do as x goes to infinity? Zero. 2 over infinity goes to 0, right? Or negative 2 over infinity as well, minus negative 2 over k, actually root k. So we're getting, for that integral, we're getting 2 divided by the square root of k, correct? And we want that, the problem told us, they said they want the error to be less than, they want the error to be less than 0.001, which is the same thing as 1 over 1,000. Let me write it that way, 1 over 1,000. So this part was given. Okay, how do you solve an inequality like this? I need to know what case. How many terms should I add so that the error is less than the given specification? Yes, suggestion or question?
Should we cross-multiply as if they were an equality?
We can do that, but be careful if you have negative quantities. Then inequality will reverse. But these are, everything is positive. K is positive, 1,000 is positive, so you can do that. So that's a good suggestion. So you're going to have 2,000 is less than square root of k. Actually like this, right? 2,000 is less than the square root of k. We cross multiply. Square both sides. What is the square of 2,000? I believe it's 4 million. Right. So this is saying that k should be greater than 4 million. So you should add like 4 million and 1 terms at the very minimum so that you're going to have such a good approximation so that the difference between the infinite sum and the finite sum will be so small. Now compared with our previous answer, we only had to add up 5 terms and we still had such a good approximation. So clearly this was a very slow converging series. And as you can see, as the power gets larger, like 1 over n to the 3 halves, the power wasn't that large. As the power gets larger, they're going to start converging faster. As that power is small, like think of the example, 1 over n to the 1.1. That power was really close to 1, so it was converging very, very slowly. But yet, it is still convergent. Okay, let me see what I want in the remaining time that I have. Okay. Would you please just write this function? Just write this one. Summation of e to the power of negative n over 2. Summation of, from 1 to infinity, e to the power of negative n over 2. I want you to do the same example with just a minute ago with n to the 3 halves. How many terms should we add? Do that one with this one. How many terms should we add? This is going to be a little bit more challenging, and I want you to ask me about it next time, and we'll talk about your answers. Okay, so work on this as your another similar example to the last one that we did. And finally, let's take a quick look at the comparison test. Once again, this is in your handout. Let's see, it's on the bottom, near the bottom of the first page. Direct comparison and limit comparison. I'm going to show you that direct comparison is really not a very easy test to use, so it's almost like not relevant. I'm going to show it to you just in case so you know what it is. But really, what we mostly use is the limit comparison test. In a direct comparison test, we already used it today. You didn't even know it. For example, when I said to you, summation 1 over n squared is convergent, what can you tell me about summation 1 over n cubed? There we were using comparison test because n cubed is 1 over n cubed is smaller than 1 over n squared. So that one converges as well. So that's all it's saying. It's saying that if you have a sub n less than b sub n, if you happen to know that the big one converges, the summation of the big one converges, then the small one has to converge also, right? Because it's smaller. If that one, the bigger one is a finite answer, something smaller automatically will be finite. On the other hand, it also says that if the smaller one diverges, then the big one clearly diverges also, right? Because if the small one goes to infinity, something bigger than that has to go to infinity as well, right? And we'll just do one simple example because I want to spend the time on limit comparison. It says, okay, given 1 over n cubed plus 5 rather, does this converge or diverge? Let's see. Which one do you think is bigger? 1 over n cubed plus 5 or 1 over n cubed? Which one do you think is bigger? Or which one is smaller? 1 over n cubed is bigger, right? Because, so I'm going to put this is smaller than that because over here you're dividing with something greater than that, right? So you're dividing by something greater, the ratio will be smaller. So this is smaller than that. Would everybody agree? So the idea is when they give you something like n cubed plus 1, you try to compare to something you already know. Okay, we know what summation 1 over n cubed is. What do we know, by the way, about summation 1 over n cubed? As n goes from 1 to infinity? That's p series, right? P greater than 1, so what do we know? Converges or diverges? Check your notes. Take a look. P series is right there in the middle of the first page. It converges, it says what? Remember the example we were doing? Right, like 1 over n squared was convergent, right? Exactly. As long as the power here is greater than 1, it converges. So you know that this series here converges. So what can you tell about this one? It's smaller. So what can you tell about that one? That one converges also because converges means it goes to a finite answer. So call it L. So something less than that has to go to a finite answer as well. So that one converges also. So here's how you would state this problem. You would say, okay, let's A sub n be the given series and B sub n be just 1 over n cubed. Then we know that summation A sub n is less than summation b sub n, since summation 1 over n cubed converges by p-series test, then so does 1 over n cubed plus 5 by comparison. So, if you're trying to show something converges, try to find a series bigger than that, which also converges, because then you can say, oh, this one is the baby one, this is the small one. If the bigger one is finite, something smaller than it has to be finite as well, right? If you're trying to show divergence, show something that is smaller than your series that diverges, and then you would say, oh, look, the one I have is bigger than that. That one diverges also. But the problem with this is, it's hard to find these series that you're comparing with. For example, this question had been n cubed minus 5. You really could never apply this technique. So that's why I don't like this test that much. Occasionally, it's good, and it's good for you to know all the tests. So under different circumstances, you can pull a different test from your tools of tests. But it's not very practical because a slight change, it makes this test unusable. It's hard to find a function to compare with. But this other one is very easy to use. This is called limit comparison test. Right on the same page in your handout near the bottom, limit comparison test. And here is what it says. If you're trying to determine if a series converges, find another series and take the ratio of them. So if you're doing the a sub n, for example, try to find a similar series such as b sub n and take the ratio. As long as the ratio goes to a finite answer, the limit of the ratio goes to a finite answer, then we are told that both of them are going to act the same way. This is how I remember this test. If the limit is a finite answer, I look at it as like a sub n over b sub n. For all practical purposes, is a finite answer, that ratio. After a certain point, yes. But in other words, this tells me that a sub n, roughly speaking, is a constant times b sub n. So if this one converges, this one converges. This one diverges, this one diverges. So they are very similar, basically, okay? If the ratio is a finite answer, then they're going to behave the same way. That's all it is saying. So question number 1, it says, indicate if this series converge or diverge. This one is very easy to use and very practical. All you have to do is look at the highest degree term on the top and the highest degree term on the bottom, okay? These are your dominant terms. The other ones become negligibly small eventually. What can you tell me about n squared over n to the 5? So look at the dominant terms on the top and on the bottom. Take the ratio of them. What do we get? 1 over n cubed. Call that your new series, b sub n. We're going to compare the given series with this one. Okay? I don't even have to do a single thing on the paper, and I know the answer. I want you to do the same, and then you can do the technicalities, okay? What do we know about summation of 1 over n cubed? Converges. Automatically, the given series converges also. Now, we have to do the technicality, though, okay? So in our mind, we have an answer. Now, let's just do the writing as we're supposed to write these things a little bit in detail. But at least you can see how easy it is to use. Like, look at the next example. Just look at it and tell me what your answer would be there. 3n over n squared. I'm going to come right back to it, to the first one. This is going to behave like which series? Look at n over n squared, which is 1 over n. What do we know about summation 1 over n? That's p series with p equals to 1. Look at your sheet if you forgot. What happens if p is 1? It diverges. If 1 over n diverges, then this series will diverge also. Okay, it's that easy to use, but we just have to do the writing now. Okay, let's go back to the first one, for instance, to do the writing. Okay, so we picked our b sub n. So we're going to compare this against summation 1 over n cubed. Now, the rule says take the limit of this quantity. Take the limit of a sub n over b sub n. That's what I'm going to do. I'm going to take the limit of a sub n is the given series. Okay, divided by B7. Technically, I should be dividing this by 1 over n cubed, but what is that equivalent to? It's multiplying it by what? If I'm dividing it by 1 over n cubed, I should be multiplying it by n cubed over 1, exactly. So what I wrote here is, this is my a sub n over b sub n. We need to find this limit because the rule says up there, it says, find that limit and verify that it is a constant. But the way we're picking these b sub n's, they will always turn out to be a constant. So this is really formality is what we're doing right now, okay? So what is this limit, by the way? What is the limit of this product? All you have to do is look at your highest degree terms. On the top, 3n squared times n cubed, what do you get? 3n to the fifth. On the bottom, 1 times n to the fifth. Ratio of the top, if the degree of the top is the same as the bottom, what will be the limit? 3. The limit is the same as 3n to the 5 over n to the 5, that's 3. All you care about is that this is a finite number, less than infinity, it's a finite answer. That means summation a sub n and summation b sub n behave the same way. And since summation of 1 over n cubed converges, the given series converges also. By which test? The overall umbrella, the bigger series was the limit comparison test. Okay? So the given series converges also by the limit comparison test. Okay? Could you quickly finish that one? We've already mentioned what the answer will be. It'll be divergent. But go ahead and pick your b sub n and do the ratio thing. We don't even need a 3 there. Just look at the dominant terms. You don't even need a constant. Say n over n squared. Let b sub n be 1 over n. And just take this ratio of a sub n over b sub n. The original one, exactly. A sub n is the given one. And dividing by 1 over n is like multiplying by n over 1. Once again, we've got a finite limit here. It's L less than infinity, so they will both behave the same way. What do we know about summation 1 over n? Diverges. So does the given series by limit comparison test. I want you to mention names. I want you to drop names. Mention the name of the test that you use because there's 50% chance that you're gonna, it's either convergent or divergent. If that's all you say, I hate to say it, but you're not gonna get any credit on the test or on a quiz. You gotta say which test you have used. If you use more than one test, please mention both names.
You have the name of the show.